Hello everyone, welcome to the module number 2 in strength of materials. In this module I will be discussing about the stresses. This is the continuation of the previous module, and in the previous module we learned how this subject is important in engineering, and we saw different examples which are related to different fields of engineering. And in those examples we basically concentrated on strength of the material. Now I will be discussing some important aspects which the design engineers have to look into when they are designing any component. I am considering the examples which are related to the aerospace engineering, and in aerospace engineering those engineers will study how to design the aircraft and what are the forces that are going to act when the aeroplane or aircraft is moving in the air. And as you see, these aeroplanes or aircraft, these are moving in air against the gravity. That means the motion of these aeroplanes or aircraft will take place against the gravity, because there is some weight that is going to act in the downward direction. And if the aerospace engineer construct the aeroplane with some heavy weight particles, then the efficiency of that aeroplane will be decreased. This is because the fuel that is required to move the heavy weight aeroplane is more compared to the less weight aeroplane or aircraft. So the aerospace engineers have to look into this aspect also, that is the weight of the aeroplane or the component with which it is made. And at the same time they have to look into the strength of those materials also. This is because when aeroplane is moving or flying in the air, then these are subjected to some wind forces. To avoid the failure of the material due to that wind forces, they should have sufficient strength. So the aerospace engineers have to look into the aspects like strength and weight, and at the same time they have to look into the cost of the component also. If they go for very high strength materials, then the cost that is required to prepare that material is very high. Then they have to think about all these aspects like strength, weight, cost, everything when they are designing any component. Okay, these are the important aspects the design engineers have to look into when they are designing any component. Okay, let me give some examples which we commonly come across in our daily life. Suppose when you are sitting on a chair or any bench, what type of stresses that chair or a bench will subject it to? When you are sitting on that particular bench or chair, then the weight of your body will act on that bench or the chair, and at the same time the reaction force will be offered by the ground in the opposite direction, and these two forces are acting towards each other, and then the material will be subjected to some compressive forces. So the stresses that are developed due to those forces are called the compressive stresses. Okay, similar, if you analyze the example which is related to the duster, which is used to rub the pencil marks or pen marks on the blackboard, then if you observe that when you are rubbing by using the duster, then the forces that are acting at the contact of this duster with the blackboard, at that contact surface there will be some shear forces that are going to act. These are the common examples which we commonly come across in our daily life. And when you are studying any subject, you please relate some of the examples in your daily life, then you can understand what that term will indicate or that concept will explain you. Similarly, if you go for the mechanics of rigid bodies, and if you take the example as the walking of a person, then you can analyze that thing as the dynamics problem. Similarly, if the person is standing or sitting, you can analyze that problem as a problem in statics. So whatever the things you come across in your daily life, all are examples of this mechanics subject, and every aspect you can apply the concepts which are related to this mechanics. That may be the mechanics of deformable bodies or the mechanics of rigid bodies. Okay, so when you are studying any concept, try to relate that concept with the examples in your daily life so that you can understand what the concept actually is. Next one. In the previous module, we learned different types of stresses, and we defined the stress as the internal force per unit area. Well, the significance of this internal force is that when we are applying some external force on a deformable body, then the particles of a deformable body will restrict the deformation that is caused by the external force. So what is the resistance that is offered by the particles inside the body, that will explain by using the stress definition. Okay, and we learned the two different types of stresses. One is the normal stress and second one is the shear stress. And if this is the cutting plane which is used to divide this deformable body into two parts, here I am showing only one part of the body, and if the stress that is developed by a force and this is perpendicular to this plane, then the stress developed by this force is called the normal stress. Similarly, if the stress that is formed by the force is parallel to the cutting section or cutting plane, then we can say that stress as the shear stress. The stress that is formed by this force V is called the shear stress, and the stress that is formed by the P is called the normal stress. This is because the P force is perpendicular to the cutting section and V force is parallel to the cutting section. That is the reason why we differentiated these stresses as the normal stress and the shear stress. Next concept is maximum normal stress in axially loaded bars. And to explain this concept, there is one assumption is there. That is, the material should be homogeneous. To explain this concept, I am considering this deformable body, and we know that every body is a combination of number of particles, whether it is a deformable body or a rigid body. And here I am saying that this is a deformable body, and we learned that this is a combination of number of particles. But practically, when we are talking about the material in material science point of view, these materials are made up of grains. These grains may have different shape and different orientations like this. If I want to explain that this deformable body as a homogeneous body, the resistance that is offered by each grain is equal due to the external force. When the resistance that is offered by the grains is uniform, then we can say that the stress that is acting on each grain is constant. So all the grains are subjected to equal stresses. So if the stresses that are acting on this grain is sigma, on all the grains the stress is sigma, then we can say that deformable body as the homogeneous. Okay, the definition of the homogeneous is like this. If the stresses that are acting on a deformable body at the cutting section is uniform, then we can say that body as a homogeneous body. Okay, this is the definition of the homogeneous. Now let's talk about this maximum normal stress in axially loaded bars. For this I am considering the prismatic bar like this. This is called the prismatic bar, and this is the axis of the prismatic bar or centroidal axis. This is because if you calculate the centroid of this cross section, that is rectangular cross section which is having the base B and height H, and it is also having the length L. This rectangular cross section is going to have the centroid at this position, that is the intersection of the symmetric axis, and this axis which is passing through this point is called the centroidal axis or the axis of that bar. This prismatic bar is subjected to the axial force like P, and here I am saying that this is in equilibrium. If you observe this figure, you can say that the forces P which is acting on either ends, these two forces are having the same magnitude and they are acting in the opposite direction. So you can say that this prismatic bar is in equilibrium because the summation of all the forces which are acting in the direction of axis will be equal to 0. And here if I assume any cutting section perpendicular to this axis of that prismatic bar, and if I want to know what are the forces that are acting at that cutting section, then I have to draw the free body diagram. And here I am assuming that this is the free body diagram and this is the axis, and here at this end we are applying some force P, and here it is said that the material is homogeneous. So at the cutting section we are going to have some grains which are having different orientation and different shapes like this, and we said that it is homogeneous. So all the grains are going to have uniform stress distribution, that is the stress that is acting on this grain is sigma. On all the grains there is constant stress that is going to act because the material is homogeneous. And if I want to know what is the force that is acting on each grain, then I have to multiply the stress with corresponding area. So the internal forces that are acting in each grain I am indicating as SI, and that is equal to sigma into dAI. dAI will explain the area corresponds to each grain. And then we said that this prismatic bar is in equilibrium. So if you consider any part of that prismatic bar, that is also in equilibrium. So the summation of forces along the axis will be equal to 0. And here I am assuming that the force which is directed in the leftward direction as a positive, so P will be positive because it is directed in the leftward direction, and the remaining internal forces are indicated as sigma equal to 1 to n SI, where SI indicates the summation of all the forces that are acting at the cutting section, and these forces are called the internal forces. So this will be equal to 0. So we are going to get the summation of internal forces will be equal to the external force. That is the reason why when we dealt the concepts which are related to the method of section, we explained that the summation of internal forces will be equal to the externally applied forces, and this is the reason why we explained that. And this SI is replaced as E is equal to sigma equal to 1 to n sigma into dAI. Okay, and this summation of all these things will be replaced with the integration definition, that is equal to sigma into dAI, and here sigma is a constant, dAI is the variable. So if I assume that each grain is having same constant area, then I can give that the sigma stress is equal to P by area. This is the definition of the stress. And here if you observe that this stress is caused by the force, internal forces which are acting perpendicular to that cutting section. So we can say this stress as the normal stress. Okay, that will be equal to the summation of internal forces by the area, and this P will be equal to the summation of internal force. And we have to define what is the maximum value of this normal stress. To define that, we have to observe the numerator and denominator terms. Here the area, the denominator is the area and the numerator is load applied. That is, this maximum stress is dependent on two terms, that is the load and the area. And here if you observe this figure carefully, then you can say that the prismatic bar is having constant cross-sectional area throughout the length. Okay, and at the same time the force which is acting along the axis is also constant. So we can define this, whatever the stress we are getting, as the maximum normal stress will be equal to P by area. You suppose you are having the cross-sectional area like this, if the beam like this. We have already seen this type of example in the previous module, where if you calculate the internal stresses that are acting at different sections, will be different. So the internal forces are going to vary along the length of the bar, and similarly the cross-sectional area is also varying. Okay, then you may have different stress values at different sections. If you want to calculate what is the maximum normal stress in this case, that is varying cross-sectional area, we have to consider the force that is acting at the cutting section, and at the same time what is the cross-sectional area. If the cross-sectional area is minimum, then you can say that it is going to have the maximum normal stress, and if at the same time if the internal forces are maximum, then also the stress will be maximum. So you have to take care of all these terms when they asked you to define the maximum normal stress. Now let us try to understand what are the complexities that involved in this coursework. And here to explain those things, I am considering the C section. And here the C section is in equilibrium under the action of these two forces P, which are acting in the opposite directions. Okay, and if I assume a cutting section AA at this portion like this, if I want to know what are the internal forces that are acting at that cutting section, then I have to draw the free body diagram. So the free body diagram is like this. Okay, this is the section AA. And what are the external forces that are acting on this part of the C section? It is only the force P which is acting on this end. And to balance this force, there will be some reaction force that is going to act in this upward direction. The magnitude of this reaction force is numerically equal to the P. So R is equal to P. And this force R is going to act exactly in the opposite direction to the direction of P. This is because to keep this C section is in equilibrium, so there will be some reaction force that is going to act at the cutting section, and this is the reaction force. And here when I am saying that this is in equilibrium, then the summation of all the moments will also be equal to 0. So if I assume this as the axis and the distance between these two is E, and the moment that is caused by this external force P is given as m is equal to E into E, and this is going to cause the clockwise moment about the point on this section AA. To keep this C section in equilibrium, there will be some reaction force that is going to act in the opposite direction, that is in the anti-clockwise direction, which is having the magnitude m is equal to E into E. So at the cutting section you are going to have the reaction force and the moment also, and this moment is called the reactive moment, and this force is called the reactive force or reactive internal force. This moment is also called as the reactive internal moment. So far we seen what are the stresses that are developed due to this internal force. Similarly, there will be stresses that are going to act due to this bending moment also. So at the cutting section you are going to have the stresses that are caused by this force, internal force, and at the same time the stresses that are caused by this bending moment. These things we are going to learn later in this coursework, but for the time being you understand what are the complex scenarios which we come across when we are dealing with the strength of materials course. Similarly, here in this example I am having two blocks. This is the block 1 and this is the block 2, and we are applying the force on this block 1. Okay, and this force is transferred to this block 2 by this block 1. So there will be some stresses that are induced in the block 2. Okay, that stresses are called the bearing stresses or the normal stress. Okay, this normal stress is also called as the bearing stress. This is because the block 2 is bearing the load that is given by this block 1. That is the reason why the stresses that are developed in the block 2 are called as the bearing stresses, because the load is not directly applied on the block 2, but that load is transferred to the block 2 by block 1. That is the reason why we are calling these stresses as called the bearing stresses. Or we can say that the stresses that are induced in the block 2 as the normal stress also, because if you consider any cutting section perpendicular to that force, then we can say that the stresses that are developed due to that force is called the normal stress. And similarly, you have learned the course which is related to the manufacturing. In that coursework, we learned different types of processes, and here I am discussing one of those processes, and this process is called the rolling process. And here this is the process which is commonly used to decrease the thickness of the material. And here if you observe, the thickness of the material is T1 before applying any force by using the rollers. Later the thickness is T2, and this T2 is less than T1. So observing this figure only, you can explain that the thickness of the material are going to decrease when we are doing the rolling process. And here the forces that are caused by these rollers will be like this. These two forces are going to act towards each other. It means this is going to cause the compression in the deformable material. That is the reason why the dimensions are going to decrease in the direction of force applied, and in the lateral direction the dimensions are increasing. So we can say the stresses that are developed inside the material or the compressive stresses. Similarly, you deal with the different types of processes like extrusion, forward extrusion, backward extrusion, and tube drawing, etc. All these processes which involves the concepts related to the strength of materials. And if you relate this with those processes with the strength of material, then you can understand what is the different types of stresses that are developed inside the material. Now, the next one is the shear stresses. For this also I am considering the same prismatic bar, and this prismatic bar is subjected to the axial forces like this, which is having the length L, base B, and height H. We saw that the shear stresses are developed by the forces which are parallel to the cutting section. So here I am assuming a cutting section parallel to the direction of force, and here I am assuming that this prismatic bar is homogeneous. It means the stresses that are acting on each grain is uniform, or you can say it is constant. And this cutting section is going to divide this prismatic bar into two parts. And if I draw the bottom part, this is the external force P, and at this cutting section the internal forces are going to act like this. Due to these internal forces, these forces are called as the shear forces. There will be some stresses that are going to act. Those stresses are called the shear stresses, and this is indicated by V by area. Here the area will be equal to length L into base P, and here the shear stresses are indicated by shear force per unit area. The area is given as L into B, and if you go back to the normal stress definition, here the area is given as the base B into height H. This area is base B into height H. This is called the cross-sectional area, and when we are dealing with the shear stresses, that is given as the surface area. This is the basic difference between the areas which are related to the stresses. Okay. Now let us try to see some examples which are related to this concept. Here I am showing one building, and this is subjected to some wind forces which are going to act like this, and these wind forces are going to act along the surface of the roof. Okay, so the stresses that are acting on this roof is the shear stresses. Okay, similarly, if you go for one of the manufacturing processes like machining, here also the forces that are going to act like this in this way, and if the forces are going to act in this direction, the chip is going to form, and this chip is moving like this. And this is the cutting process which is commonly observed in turning, drilling, boring, etc. In those operations, the material is removed from the workpiece as in the form of chips. So these materials are subjected to the shear stresses. And here the force applied by the tool is greater than the shear strength of the material. That is the reason why the chip is formed. Okay. And similarly, in this example, I am taking two different bars. This is the first bar and this is the second bar. Okay. And these two bars are glued together and at this section AA. And these two bars are in equilibrium under the action of these two forces. Then if I want to know what are the stresses that are acting at the glued portion, it is the joining portion between these two surfaces. And if I draw the top view of this second part, and at this portion the shear stresses are going to act, and here we assumed that the shear stress is those two plates are homogeneous, so there will be uniform shear stresses that are going to act. Then the shear stress is given as the shear force by area, and the area is taken as this contact area. If this is base B and this is the thickness, then this area will be equal to B into P, that is the contact area. And this stress is also called as the average shear stress. And similarly, in this case also, I am having three plates. This is first plate, this is second plate, and this is third plate. This second plate is glued to the first plate at this section, and third plate is glued to the first plate at this section. At the contact surface, there will be shear stresses that are going to act, and we can say that this first plate is subjected to the shear stress at the top fibers and the shear stress at the bottom fibers. So this plate is said to have double shear, and this plate is said to have single shear, because there is only one shear stress that is going to act on the top fibers. But in this case, we are having two different types of stresses, one at the top fibers and one at the bottom fibers. So we can say that the plate 1 is subjected to double shear. Okay, and in this case also, the average shear is given as shear force by area. Area will be correspond to the contact area as we seen in the previous example. For engineering application, we commonly come across these shear stresses when we are dealing with the welded joints, nut bolt joints. And here, to explain the nut bolt joint, I am considering this example. These are the two plates which are put together by using this nut bolt arrangement, and these two plates are subjected to the forces which are shown like this. This is the force PP, P like this, and this total arrangement is in equilibrium under the action of these two forces. And if I assume a cutting section like this at this part AA, then at that portion there will be shear stresses that are going to act on the bolt, and at the same time the force is transferred from this plate to the bolt. So there will be some bearing stresses that are going to act on the bolt also. So if I draw the free body diagram of the bolt, there will be some bearing stresses that are going to act in this direction, and at the joining of two layers at that section there will be shear stresses that are going to act. So the bolts are subjected to the bearing stresses, and at the same time they are subjected to the shear stresses also. So from these examples you can understand that whatever the part you are considering, it is subjected to both the normal stress and the shear stresses also. Okay, which explains you that there is not only one particular stress that is going to act, but the combinations of stresses are going to act on a material or a body. Next one. Till now we learned that what are the stresses that are going to act when we consider the cutting section parallel to or perpendicular to the axis of the bar. Now I am going to discuss about the cutting section which is inclined to the axis of the bar, and this cutting section is going to divide this prismatic bar into two parts. And here also I am assuming that prismatic bar is homogeneous and this is subjected to some axial force like this. And if I draw the two-dimensional view of this figure, and this plane, cutting plane, looks like a line, and we are drawing the two-dimensional view, and the forces that are acting on this body is P. Due to these forces, this bar is in equilibrium, and this is the cutting section A. And if you want to know what are the stresses that are acting at the cutting section AA, then you have to draw the free body diagram. And here I am considering the left hand side of the section. This is the force P which is acting along the axis of the bar, and at the cutting section we are going to have the internal forces that are caused by each grain, and if you add those forces, then the summation of all the forces will going to act in this direction. Let's suppose that summation will be P dash, and the P dash will be numerically equal to P, and this is going to act in the opposite direction to the force, externally applied force P. And only we can say that this part of the prismatic bar is in equilibrium. And also when these two stresses are acting along with the same line of action, then the moment that is caused by these two forces will also equal to 0. Okay, so we can say that part of the prismatic bar is in equilibrium. This is the force that is going to act at that cutting section. And if I assume this area as A, and it is also said that this cutting section AA is making an angle theta with the vertical, and here we know two different types of stresses, that is normal stress and the shear stress. Normal stress is developed by a force perpendicular to the cutting plane, and shear stress is caused by a force parallel to the cutting plane. So to know what is the magnitude of the normal stress and shear stress, we have to resolve this force P dash along the cutting section and perpendicular to the cutting section. So for this I am choosing one reference coordinate axis like this. This is the x dash axis and this is the y dash axis. Y dash axis is parallel to the cutting section AA, and x dash axis is perpendicular to the cutting section AA, and this is 90. So this x dash axis is going to make an angle 90 minus theta with the vertical. So the angle made with the horizontal will be equal to theta. Then if the angle made by the force with the horizontal is theta, then the horizontal component of this force is given as P dash cos theta. That is the force that is acting in the x dash direction, and the component of the force in the y dash direction is given as P dash sin theta, and this is acting in the direction opposite to the y dash direction. And if you know the area at that cutting section, then we can define what is the magnitude of the shear stress and the normal stress. To define that, we know the cross-sectional area of the prismatic bar as A. So if this is A, this cross-sectional area is A, and it is making an angle theta with the inclined axis, and if I want to define this area, it is given as A by cos theta. Okay, this is the hypotenuse and this is the adjacent side. So if the adjacent side is having the magnitude A, then that hypotenuse is going to have the magnitude A by cos theta. So we know what is the magnitude of force that is going to act along and perpendicular to the cutting section, and we also know what is the cross-sectional area at that cutting section. So we can define the normal stress which is acting in the x dash direction, that is given as sigma theta theta, that will be equal to P dash cos theta. And if you observe this P dash cos theta, this is the internal force that is acting in the x dash direction by what is the cross sectional area, it is A by cos theta. So sigma theta is given as P dash by A cos square theta. Similarly, tau theta theta is given as P dash sin theta. This is negative because it is acting in the negative y-axis direction by A by cos theta. So this will be equal to minus P dash by A sin theta cos theta. So we defined the magnitude of the normal stress which is acting on the inclined plane. Similarly, tau theta theta. Similarly, if I ask you to calculate what is the stresses that are acting on this cutting section BB, similarly you do the same process what I did for these calculations, and here this is the free body diagram. Here I am giving the free body diagram. This is the axial force, this is the y dash axis, and this is the x dash axis, and this is making an angle 90 minus theta. So the force, internal force P dash is going to make an angle 90 minus theta with the x dash axis, and so this will be P sin theta, it is going P dash sin theta which is going to act along the x dash direction, and P dash cos theta is going to act in the y dash direction. And similarly calculate what are the shear stress and normal stress that are acting at the cutting section BB. And here these cutting section A and BB are perpendicular to one another, and so you have to get the sigma theta theta as P by A sin square theta, sigma 90 minus theta as P by A sin square theta, tau 90 minus theta as P by A sin theta cos theta. And here the cutting section BB is like this and AA is like this, and we calculate the magnitude of the normal stress as sigma theta theta, it is equal to P by A cos square theta, and the shear stress is P by A sin theta cos theta. This is tau theta theta. And here also we are going to have the shear stress as tau 90 minus theta as P by A sin theta cos theta, and sigma 90 minus theta as P by A sin square theta. And if you observe the magnitude of the shear stresses, these two shear stresses are acting in the mutually perpendicular planes. So in the previous module we learned that the shear stresses which are acting on mutually perpendicular planes should be equal, and the magnitude of these shear stresses will be equal to P by A sin theta cos theta and P by A sin theta cos theta, and tau theta is going to have the negative direction compared to when it is compared with tau 90 minus theta. So one stress is going to cause the clockwise couple and one stress is going to cause the anti-clockwise couple. So that is the reason why there will be negative sign on the other part of the shear stress. If you want to write the stress tensor matrix, that is given as sigma theta, tau theta, 0, tau 90 minus theta, sigma 90 minus theta, 0, 0, 0, 0. Okay. And here remaining stresses are equal to 0 because we actually consider the two-dimensional case for calculating these normal stress and shear stresses. That is the reason why though we are getting 2 by 2 matrix. And if you are having the only two normal stresses that are going to act in two directions and one shear stress, then we can say that stress system as biaxial stress system. Bi means two, so there are two normal stresses that are going to act in two directions. Okay, that is the reason why we are having two normal stress and two shear stress, but the shear stresses which are acting on mutually perpendicular planes are equal. That is the reason why we are saying that when we are dealing with the biaxial stress system, it is going to have two normal stress and one shear stress. Similarly, if you see the examples which I explained earlier, in this only one stress that is going to act along the axis. So sigma 0 0 0 0 0 0 0 0. This is the stress tensor matrix for this particular figure. So this type of stress system is called as the uniaxial stress system. Uni means only one stress that is going to act. That is the reason why we are going to have only one normal stress that is going to act in the further particular configuration. Next one is the member strength as a design criteria. Here I am showing one figure which is related to the uniaxial case, that is the force that is applied in this direction, that is in the tensile case. So when the forces that are applied in this direction and these forces are gradually increased, then the materials are subjected to deformations, and if the load is greater than the strength of the material, that is going to break into two parts like this. The load at which the failure of the material will take place, that load is called the ultimate load. But when we are practically dealing with the machine parts or any component, these are subjected to forces in all the directions, and the stresses are going to act in all the directions. And also there are different types of failures like fatigue, creep, etc. These things you are going to learn later in this coursework, and due to all these cases, the failure of the material takes place before the load reaches the ultimate load, and that load is called the allowable load. First, basically you understand the failure of the material is going to take place before it reaches the ultimate load. Okay, that load is called the allowable load due to the reasons like fatigue, creep, which you will come across later in this coursework. So they introduce two different terms like factor of safety, which is given as allowable load by ultimate load. This is also given as allowable stress by ultimate stress. And there is one more term called margin of safety. Margin of safety, that is given as factor of safety minus 1. And this margin of safety is commonly used by the design engineers, which is related to the aerospace, and when they are designing any aircraft, aeroplanes like that, they use this term margin of safety to define the strength of the material. Remaining all cases we go for this factor of safety, which will indicate what is the allowable load which the material is going to take care. Okay, this is all about the stresses. Thank you.